It's always so lovely to host you every Wednesday right here on these Digital Earth Africa live sessions. Greetings, fellow leaders from the African continent and across the world. Welcome to yet another live session today. My name is Maud Nale. I'm the communications lead at Digital Earth Africa. And during today's live session, we're going to be talking all things flood risk monitoring. I'd love to go straight into it and introduce our presenter today. She is no stranger right here at Digital Earth Africa family and on these live sessions. Her name is Victoria Kartoza, and she is a junior developer. Her name is Victoria Nima, and she is a junior developer at Kartoza. And she's going to be talking about using the Digital Earth Africa platform, more specifically the sandbox, to monitor flood risk. Victoria, if you're ready, the virtual stage is yours. Over to you.
It will be flood risk modeling and flood monitoring also. Let me set this. The notebook we are going to be using is the notebook developed by AFRIGIST for their training session that they held earlier last year. For those who are new, the notebooks are used within the Africa Sandbox, which is a cloud-based computational platform that operates through a Jupyter Lab environment. It provides a limited but free computing resource for users to be able to explore the data that Africa provides, including the products and services that Africa has. Speaking of floods, there has been noted an increase in intensity and frequency of natural hazards across the globe. In Africa, floods are the most important hazard in terms of frequency and magnitude, and occur more often than drought and war, with more devastating effects. Urban areas are highly prone to be affected by floods. This is because although they account for a very small proportion of land cover, the influence they have over the environment due to their concentrated populations and economic activities make them very vulnerable to the impact of floods. Disruptions in such areas lead to a very high impact on the economy, people's lives, and on the environment. Also, urbanization is a major contributing factor to flooding in developing countries in Africa, because urban areas tend to be built near water bodies, which ends up restricting flood water movement. All these factors make flood monitoring and modeling for urban flood risk management very important. The notebook that we'll be reviewing today plays a very important role in measuring the following SDG indicators. This is 2.4.1, which is the proportion of agricultural area under productive and sustainable agriculture, and 15.3.1, which is a proportion of land that is degraded over total land area. When it comes to flood monitoring, synthetic aperture radar, or SAR data, in short, is usually preferred over optical data, the most commonly known being Landsat and Sentinel-2. This is because of the ability of microwave radar to differentiate clearly between water and other non-water objects. SAR backscatter from water is very low since the water surface is smooth. Hence, flooded areas appear as dark tones due to the low backscattering response, where land or other non-water surfaces appear as bright tones because of the rough soil surface and the vegetation produce diffused reflection, resulting in a stronger backscatter. Digital Earth Africa provides analysis-ready Sentinel-1 data for cost-effective and accurate flood monitoring, particularly in areas where rivers are not equipped with river gauges. The notebook starts off by defining the area of interest. In this case, our area of interest is the Lokoja area, where the confluence between the river Niger and river Benue occurs. The time range that we want to analyze for is September 2021, July 2021 to September 2021, as there was a flooding event that occurred during this time range. We first start off by loading Sentinel-1 data using the load ART function. As you can see from the images plotted on screen for the VH polarization, we can see the dark areas are clearly defined as water, with the bright areas being urban areas, highly likely urban areas, and the other surfaces being other non-water surfaces. The next image also shows the VV polarization for the time range that we loaded. One thing you'll note is that VV backscatter is usually significantly higher than VH. This is because the scattering mechanisms that each band responds differently. Also, the range of the backscatter values is higher for VV as opposed to the VH polarization. The next step in the notebook is to apply the Lee speckle filter and convert the digital number values to decibel values. As compared to the previous images, the images now appear brighter, and the water and non-water surfaces are very clearly distinguished between with the speckle filter and the conversion to decibel values, as opposed to the other images that we loaded previously. We can see the same for the VV polarization. The next step is to select what we call our pre-flood and our post-flood images. I'll go back to the previous slide. You can see from this first image you can see a clear distinction where there was no flooding occurring, and now to the final image where you can see around the middle part that there is quite heavy flooding. Using this selection, we now have our pre-flood and our post-flood images, as you can see on screen. The next step will be select which polarization band we will use going forward for our flood monitoring. In this case, the VV polarization is preferred because it has a wider range of backscatter values from vegetated land surfaces compared to the the VV compared to the VV. As you can see clearly in the plot below, the VV, which is orange, has a wider range compared to the VH backscatter values, which are in blue. Once we select our polarization band, which is the VV, we then use a threshold to separate water from non-water. This threshold is determined using the threshold minimum function from the ski image package. The value that we end up with is, for this particular area of interest and time range, is negative 14.231. Using this threshold, we then threshold the pre and post flood images to get the water extent. So the water extent in July is our pre-flood image. You can see the natural path of the river. Then we have the water extent in September, which is our post-flood image, and you can clearly see the areas which there is detected a presence of water which was not there before. Using these two images, we can then detect the change in water extent. From the color map that you can see on the bottom left, we have the blue indicating the water to water areas. So these pixels in our images remained classified as water when we applied the threshold to our pre and post flood images. The yellow, which is not quite clearly seen except for this particular spot, is where water pixels classified as water in our pre-flood image were then classified as no water in our post-flood image. The pink areas are what will be of most interest to us. So these are pixels that were classified as not water in our pre-flood image and classified as water in our post-flood image when we applied the threshold. which means that highly likely these areas are what are the flooded areas. We then use the ESA world cover dataset for 2020 to get the urban areas and cropland or vegetated areas for our area of interest. And then we superimposed the change in water extent image that we have. So we can clearly see the green areas of vegetation, and where you can see an overlay of pink is where these areas, vegetation areas were flooded. You can also see here on the side where we have the urban areas as red pixels, and you can see along the river where these areas were flooded. Up next in the notebook, we did a flood risk assessment using elevation data. Digital Africa provides a variety of data sets. So we have the Copernicus and the SRTM digital elevation models. In this case, we use the Copernicus DM for the Lokoja area, and we determined that or classified that areas with a high risk of flooding are areas with an elevation of less than 50 meters, and areas with a medium risk of flooding are areas with an elevation of 50 meters or greater, but less than 100 meters or equal to 100 meters. By applying this threshold, we got the image on the left. Yes, the left, where we have combined using the ESA world cover data for urban areas and cropland areas, and we now defined the red areas are the built up areas which are highly prone to flooding. We also have the yellow areas, as you can see here, which are the cropland areas which are highly prone to flooding. We also have the purple areas which form majority of the image, which are urban areas which have a medium risk of flooding. Then we have the light green areas, as you can see where the mouse is pointing, that show the cropland areas with a medium risk of flooding. Then we have the brown areas which, based on the threshold we applied, are highly likely not to be affected by any flooding. So these are the unaffected built up areas indicated by brown. And then we have the dark areas, which are quite minimal, but you can see them along the edges of the image. So these are cropland areas which are highly likely not to be affected by any flooding. From this image, we then got the following statistics indicated by the bar graphs. So for the first bar graph, we have the total affected urban areas. So you can clearly see it's about 20 kilometers squared, which are areas, the total urban area as per the ESA world cover for our area of interest. Then we have the total area that is at high risk of flooding, but majority of this area is at medium risk of flooding. And then we have a minimal unaffected urban areas, as compared to the cropland, where we have the total cropland indicate about 14 kilometers squared. Majority of the cropland is at high risk of flooding, with followed by the cropland that is at medium risk of flooding, and then we have at minimal the unaffected cropland area. These are following at the important links to the various platforms that you can be able to do your analysis on. So we have the analysis sandbox, we have the map, and we have the GitHub platform where we keep all our Africa sandbox notebook. To join the community or ask questions when you encounter a problem, please feel free to use the help desk. You will be able to get someone who will assist you with your issue. We also do have the Africa training course the link is provided on screen. We have the Intro to Sandbox and the Masterclass, where it is a self-paced courses that are free to access, fully online, that you can be able to use to understand the platforms better and be able to use our notebooks and other data sets for your own analysis. There's a certificate of completion that is awarded upon the completion of the exercises. We also have the Africa website, and we also offer these live sessions every week. The email address that you can use to contact us is on screen, info@digitalearthafrica.org. Thank you for your time. Over to you, Maud.
No, it's actually, thank you so much for your time and for sharing your experience and expertise with us, Victoria. It's always so lovely to have you here on these sessions, sharing with our user community. Today was all about monitoring flood risk and flood modeling. I'm not sure if any of the leaders on the call have a question or comment for Victoria at this point. In the chat box, I have dropped a link, or our capacity development lead has dropped a link to our recordings if you want to catch up on this. If you're looking for the presentation, we will share it as part of our user community group. Please hop onto the chat box and join that community so that we can keep these conversations going. And a reminder, it was on Victoria's presentation that the learning never stops. This may not be of interest to you or this particular topic, but there may be something else that interests you. So please hop onto our website, learn.digitalearthafrica.org. We have an array of online courses that are available to you in English. Some of them are also in French, and you do get a certificate of completion when you are done with that course. So we look forward to also seeing you on one of our online programs in the near future. I've noticed that there aren't any questions or comments for you, Victoria, which means you did a very good job. So thank you so much to you. We always host our user community, but we also have very special guests. Thank you. It's with us. Leaders, we never want to end these sessions without giving you an opportunity to connect with us. And so you can do exactly that. In addition to the user community group, which is in the chat box, you can connect with us with any of the platforms that are on your screen right now. Our website is www.digitalearthafrica.org. You can also email us info@digitalearthafrica.org. And reminder, if you want to take on any of those online courses, it's not on here, but it's learn.digitalearthafrica.org. And we're also on social media on Twitter, LinkedIn, as well as YouTube, where you can catch up with all the sessions that we've hosted since these sessions started about 3 years ago. And the name there is Digital Earth